Sorry about that delay. My laptop actually died during my last meeting, and so it takes a long time. It has to boot up. So a lot of things to start up. So we're going to start off today talking about experimental design, and then we're going to talk about cloud computing and AWS and some things like that. So I have not had time to review your reviews of other people. I looked at a couple on Sunday morning. Looked like most of you were giving meaningful and good feedback, so things look like it's okay. I have not finished my reviews of your paper. It was a long weekend of grading, as I had midterms from one class, 45 papers in another class, plus this class. I didn't get through them all. But I will try and get through yours by Wednesday of this week, so you all have feedback. But I'm not going to set the final due date. It'll be a week after whenever I finally post all of the reviews. So it's at least a week out. In fact, because I have to teach tomorrow, it will not be until probably a week after Wednesday, but it might be a week after Thursday or Friday, depending on how slow I am. I also have a thesis defense this week. So you can keep working on it based on the feedback you have, and then refine it and whatever. But we're going to go ahead with the next parts of class. I just can't wait until I'm caught up to do that part. Any questions on the reviewing assignment? So most of the people who did not get assignments aren't here. Did anyone have none that they got to review? David, did you get to review any yet? They were still missing? Well, many people had one, or a number of people had one, but both of you, David's, were missing. So send me mail, the three of you, so I don't forget, and I'll give you a quick, you guys can exchange money among each other. There were 6 people who hadn't turned anything in, so I randomly assigned among that group of 6, but apparently I chose badly. I was hoping that if I randomly chose, you'd get one. So if you haven't got any feedback, all 3 of you send me mail, and I'll exchange among you 3. So. Yes. So if it's a really good paper, you start off by saying, this is a really good paper, right? Here's what I liked about it, okay? So you can give them some positive feedback, right?
So positive's always good, right?
Positive's always good. So almost everyone likes to hear positive things about their paper. I don't know anyone that says, oh man, they missed this positive review, I feel guilty now, right? It's just not gonna happen. But my guess is you can find something to say to make it better, right? I mean, it might just be as simple as, this figure might be better if it was here or if it was done different. So whatever improvements you can give them. But every now and then there's a paper so good, you really can't. So it's sort of sad as a conference reviewer, right? When you get this review that has 4 lines and they're very positive, it's very good, but then you get this other review that's really negative, right? And so then you have to balance them because the negative one is so voluminous. The positive one was positive. So you have to figure out where to go. So, but give them feedback, not just that it was good, but here's what I really liked about it. Because then if they get negative comments from anyone else, they can balance them where you said, this is the really good stuff, which pretty much means don't cut this stuff out, don't mess too much with this. And if there's sections you didn't talk about and somebody else said this section needs help, then they know that section needs help. So be specific in what you said was in a positive way. Other questions from the reviewing point of view? Did you guys see, because actually I haven't used Canvas's anonymous reviewing before. Can you see the reviews you've gotten of your paper already? So I wasn't sure if that happened before or after the reviews were due or when they were submitted or whatever. So are you finding those reviews helpful? Okay, and your review, you see the reviews as anonymous. I told people if they wanted to break anonymity, so you can say, right, if you have questions, ask me, Bob, right? That's okay. This is not like a review where you have to be anonymous. But and if you really can't understand your reviews and you want to ask, then send me mail and I can ask the anonymous reviewer, which is actually what happens at our conferences as a meta reviewer. If people say there's a problem with the reviews, it goes to me as the meta reviewer and then we work it out. And there's normally another interaction with the reviewers. Unfortunately, in the conferences, the authors never hear back from the reviewers. They only hear back from me as the meta reviewer. So I will ask the reviewers, I'll get some answers, and then I can post an answer. So it's sort of indirect, but it still sort of works. Okay, so we've talked two weeks now about experimental design. And to be honest, we talked about the role of experimental computer science and some issues in designing experiments. But neither of those lectures are what people in other fields of science would call experimental design. So today's lecture is more traditional experimental design, and you'll sort of see where that comes in. Everything else we talked about was designing good experiments. This is the sub-area called actual experimental design, which changing the word order is very different. Come on. So when we talk about what is an experiment, okay, from a, PowerPoint is. This is what happened when you choose random effects. I should have not done that, but normally I just say fly in. I said it like came up with random mode. It's like fine, choose random. I don't care. Bad choice. So an experiment is something where we control one or more independent variables to test a hypothesis about a dependent variable. Okay, and again, I want to start with this because we're going to talk about design. We want to figure out how to design it to manage the testing we want to do on the experimental variable. So don't view it as an experiment means run a bunch of stuff and compute a bunch of numbers, because that's not designing an experiment. We want to understand what's independent, what can I change, and what's dependent, what changes do I expect. And you should always be starting out with, different but still equally bad. So if our claim is that if I manipulate, and by the way, in doing this one, I'm going to use terminology that comes more from the medical or psychology side, because this is where experimental design is more commonly found. And if you go to read any of these papers, these are the terms they will use, and I will try to relate them back to computer science. So if we talk about the manipulation of a treatment variable X followed by the observation response Y. So the nice thing about this is instead of talking about independent and dependent, now we're going to talk about a treatment. I give you medicine, and I observe your response, right? That's, I think, a little easier to keep track of than independent and dependent. The treatment is what we give you. That's the independent variable. The dependent variable is the response, the observation of do you get better or whatever is going on, right? So maybe that'll be easier to remember than the other two. So our goal is to control the experiment's going to design to control the variables from to help establish our causal relationship, right? There's a lot of variance. We want to minimize the variance, and we want to do something such that if I make this change, and I make this observation, I want to hopefully get something that's not just correlation, but is causal. But that's a lot harder, and we'll go back and forth between it. But ideally, that is our goal, is to control as much as possible so that we're not getting, at a minimum, unseen correlations. So if I change 4 things at once, it's really hard to figure out what's going on. If I change one thing, then I have a better chance if everything else is held the same. But not in all situations can I do that. So we're going to want to try to minimize those to help formulate what might be a causal relationship. By the way, does anyone know how could I prove it's causal and not just correlation? We haven't had this conversation yet, but before I get to it later, how do I prove causality and not causation? Or sorry, correlation. The p-value? No, the p-value tells me how likely is it that I see this as being random. Okay, so no one has the answer. It's okay. We'll get to it later in today's class. I just wanted to see if this is something you've already covered, but no. So we have to remember that an experiment can only reject our hypothesis. That's what the p-value lets us know. What's the likelihood that this could have occurred by random chance? So if it can't be rejected as being from random chance, then clearly we haven't shown causal relationships. So our goal is not to do, so if I just sort of take what's called descriptive research, okay, I provide a snapshot of some aspect of the system at some point in time, okay? This might also be called benchmarking. I run my system, I measure a bunch of things about that. There's no real hypothesis there, there's no experimental design. That doesn't mean it's not useful, okay? It can actually be very useful to benchmark the system, make some changes, and benchmark the system. But if I benchmark it, and I make 25 changes, and then I benchmark it and it's better, I really can't argue which of those 25 or which combination of those 25 caused the change, because I changed a whole bunch of things at once. So part of what you want to be doing when you're doing this is to try and reflect designs that actually go through this step by step. Unfortunately, as we've seen already, humans tend to assume temporal relationships are associated with causality. So if I have the system benchmarked, I make some changes, and I run the system again, humans will assume that some subset or the totality of those 25 caused the change. Okay? Unfortunately, if I actually tell you an algorithm for evaluating stocks, right, and I measure it one day, I make a bunch of changes in my code, and I measure it another day, the stock market changed too, right? Not just what changes I made. So you have to be cognizant not just about when you benchmark your descriptive research, the stuff you did, but how much did the rest of the world change? If I were to do something that depends on weather, and today is much warmer than yesterday, I'll get different answers even if I ran the same code. So you want to try and design, how do I make stuff happen? So we really want to, in this part of the class, we're ignoring descriptive research and such benchmarking. Doesn't mean it's not valuable, but if I don't design the experiment, then I'm not running a designed experiment. It's not doing experimental design. So what constitutes causality? Causality is that a change in one variable will produce a change in another. If I change A, B will change. Okay. Is that really causality? Anything else I need for it to be causality? No, I don't have to create something. Right? Well, I'm creating a change, right? So there's always a creation of something. There's a creation of a change. Right, so if I don't change if I don't change the causal variable, the other variable shouldn't change, right? So at the broadest level, causality is a condition of a precondition influencing a variable interest. If I give you the treatment, you will get better. But if I give you a sugar pill and you get better anyhow, right, then the treatment might not have had any difference, right? We call that the placebo effect. Turns out that, oddly enough, giving you a pill that has no effect, it's just sugar, will actually, for many things, make people get better compared to not giving them any pills. And it may or may not be as equivalent to giving them actual medicine, right? So just the fact that in time I gave you a pill and you got better doesn't mean there's a causal relationship, okay? So the sequencing in time isn't sufficient. The important part of causality is no other possible explanation, okay? There's a couple ways we can test for that. So a common one is to sort of say, okay, I'm going to make two changes in parallel to two different equivalent populations. I give one group placebos, sugar pills. I give the other group real medicine, and I see if the group with medicine actually gets better faster, for example, than the group with the placebo. Okay? And in fact, I can then often do what's called an exchange, where I take the two groups, and now I give the group that was getting a placebo the real medicine, the group that was getting medicine a placebo, and I see if the people now getting medicine get better, and the people who are now getting placebo stop getting better and maybe even get worse if I haven't cured them. Right? So there's a whole bunch of things we can do to sort of make sure there is no other possible explanation. But a sort of minimum version of that is I have to give it to some things, give the medicine to some people, and not to others. Because if I give everyone the medicine, I can't tell is it the medicine or time. Okay? I can invent something that will help you get over the common cold. And I can give it, anytime you have a cold, I will give it to you. And I can guarantee that within 10 days, if you have the common cold, it will have cured you. Of course, anything will in 10 days because that's the 7 to 10 days is the length of the common cold. So it doesn't take any medicine. To be honest, this is where a lot of wives' tales and old wives' tales come is, right? That if you do this, right, well, by the time you decide you have the cold, you've actually had it for 2 days, you do this, yes, you'll get it better. I can take apple cider vinegar. Whether or not it matters or not, I can pour it on my feet. It'll probably still get better, right? So you got to understand that causality means showing that there is no other possible explanation. The word no is very strong here. So if you have to make it that any other possible explanation is extremely unlikely, which we can do with statistical tests, then we start to approach what we normally get to an experiment. So the no here is statistically unlikely to occur. Okay. So if we wanted to talk about something from an HCI point of view, that attitudes will affect people's behaviors. So how many of you like Microsoft's ribbon? Microsoft Office has this new, the ribbon. I mean, most of you were probably using Office before the ribbon came out. How many? Right? How many of you liked the ribbon when it came out? Okay, none of you. So Microsoft's internal research showed that over 85% of the people significantly preferred the ribbon over the stuff they had before. Okay. So, and they believe that it was because of the ribbon. Yeah, when it came out, it's like, what? Now, it turns out that when Microsoft did their study, the ribbon ran on, because of the way they were doing their testing, the ribbon was actually running on faster machines with bigger screens and a newer version of the operating system. So people thought the ribbon was much faster because it was running on faster processors. They thought it was easier to navigate, maybe because it was much bigger, right? They were working on like HD displays compared to 1024 by 768 or whatever. So there were a bunch of things they did in their experimentation that was really pretty lame, and then concluded that the ribbon was so much better. And they launched it with fanfare, saying this is so much more efficient, people will love this. And they had a hard time understanding why the community didn't agree with it. Okay, so, but the attitude was also, all the people Microsoft tested this on in the early days were other Microsoft employees, right, who were tired of the old style. They'd been using it forever. And to be honest, almost anything new was better, right, because I've been doing this way for a long time. So their attitudes also affected their behavior. Because they were Microsoft employees, they actually spent time to read the manual, right, that most of us didn't, right? And I can't find anything on the menus. They keep changing. The ribbon's like, one time it's over here, and another time it's over here, because it's contextually dependent, right? And if you read all the manuals about why they do those things, so that when you're doing these kinds of functions, they'll be over here, and we're doing these kinds of functions, they'll be over here, there's a rationale. It might make sense. But for most other people, we didn't have the attitude of, I want to learn this because this is something new for Microsoft. We just tried to use it, and we were unhappy. Right? So experiments to evaluate HCI stuff, you'd be very careful what attitude you instill in people you're going to run them going through. So the next thing we have to worry about is the direction of causation issue. So really, if you want to talk about causality, you really should draw on a logic or some previous theory that says whether one variable is relatively fixed or unalterable. Because if I take a variable that has causality in the forward direction, chances are really good there's correlation in the reverse direction. So if I run it the reverse direction, I might still see an effect. It's just not causal. So ideally, causality comes in what's going on. So if a time lag exists between the cause and the effect, then the causal variable should have a positive association with the effect variable lagged in time. Okay, this is straight out of, and I can't remember it's actually the name of the book is Experimental Design. I want to put this one out because this is just wrong. First of all, I can have a negative association with a variable. So in lots of brain studies, right, we actually know, right, light happens, and then sometime later, parts of the neurons in your brain light up. Okay, they are causal. Neurons showing up in your brain will never make light happen in the real world, in the outside world. Right? So we know the causality path. But sometimes lights happening depress parts of your brain. Right? It's not always that they become active. Sometimes they become inactive. Because the activity that was going on, when I make another stimulus happen, your brain shifts from one activity to another. So you have to be a little careful when they say positive association. Okay? Positive is true if I don't think of it as a sign, but think of there will be an association, whether or not the sign gets bigger or negative, right? Absolute value, a whole bunch of things will go on. So you got to be a little careful how some of these people refer to it. But more importantly, temporal correlation does not equal causal. Okay? If I actually have been showing you a strobing light, the neurons in your head will start firing in anticipation of the next flash of light. And if I slow down the light a little bit, right, now your brain pulses will precede the light. Okay? So in time, your brain is reacting before the light gets here, as though maybe from a causal point of view, my brain is making the light flash, right? It's not actually happening, right? But there's a lot of things where patterns and predictions start happening, and you can get things where there's a temporal correlation of A follows B, but B is not actually, so, A following B, right? So maybe B follows A is the normal way, right? Right? But A is not causing B. A is just happening in time before B does, right? And so we have to figure out where it goes on. And so one of the classic ways of first drawing these, right, is what we call a causal diagram. And it is a causal diagram. We actually, and we'll go through a bunch of formal rules, but in this diagram, we have variables, A, B, C, D, E, and arrows. And we draw an arrow when A causes C, A causes B. And notice in this diagram, there's no arrow between B and C. Variables don't have to be connected. In fact, if A causes both B and C, what do you think will happen between B and C? So, since I have arrows here that says A causes C, A causes B, what do you think will be the relationship between B and C? They're equal. No, causality doesn't mean it does exactly the same thing, right? So if it gets hotter, the CPU in your computer will slow down. If it gets hotter, the chance of your disk drive failing goes up. So temperature causes both of those, but they're not the same thing. They're correlated, right? There will be a correlation between them. Why? Because whatever A does, B and C are going to have some reaction. And therefore, if I just look at the reactions of B and C, there will be a variable, there will be a correlation. In fact, lots of correlations occur because there is an underlying, what we call mediating variable that may or may not be represented that says these two things are correlated. So one possibility is there's some super variable that influences both of them that actually is causal, right? And very often, in fact, once you start drawing these diagrams, the goal is to look for those things and say, I've got a correlation between B and C. I cannot actually, in a theory, say there's any reason that my disk drive failure should be associated with the CPU slowing down, right? That just doesn't seem to make any sense. So there must be some other variable, if I'm looking at a lot of data, to sort of say, okay, if these are correlated, what are they both being driven by? What's the overlying factor that's driving? So you can look at these diagrams and look for potential problems. So if we started the diagram without the A, and we just had sort of B and C as a correlation, then we want to look for it. So in this diagram, A causes C, C causes D, D causes E, and C causes E. What do you think it means when two different things cause E? It's not causality. Well, in some sense, it is causality. So I'll go back to medicine again, right? So if I were to give you two different things, right, either of which by themselves will not make you better, but the combination makes you better, then the combination causes you to get better. And there's a number of cases where that kind of stuff shows up, where I need two different drug interactions to make something happen. So you can have causality that requires both of them to happen. Okay? You can even have causality in a broader sense. For a particular situation, D might cause it to happen, or C, right? So what we can't tell from this kind of diagram is causality D and C, or D or C, right? For a single instance, it might be sufficient for either D or C, and in many instances, sometimes it's D, and sometimes it's C, and sometimes it's both. So causality diagrams aren't quite enough to say it's the only way. Now notice that is actually not quite consistent with our definition of no other possible explanation. So we weaken that a little bit when there are two possible explanations that we cannot separate. We'll still say it's causal, and normally what we say is it's causal on C and D. You can actually run an experiment to find out if it's just C or D by giving them just C's or giving them just D's and sort of seeing does that make things better. You have to be a little tricky. There's lots of things in the world of medicine and some things in the world of computer science where populations differ. So if, for example, you have a particular disease, then this medicine might not work for you and work for a bunch of other people, but a different medicine might work for you and not work for other people because of your genetic variations. We're not all the same. Well, not all software is the same, so some of the same kinds of things happen. You can get causality. For example, a virus that will cause an infection in Windows may or may not do so in Mac, and vice versa. Right? On the other hand, a virus that affects a website running on a PowerPC and a website that's running on an Intel processor might still exist because it's not attacking the processor level, it's attacking, say, the PHP level. So you can change levels and get all kinds of answers to what causality means in these. So when we talk about causality diagrams, as I said, we talk about nodes and vertices. It's important when you're drawing these that they really should be clearly understood by others. The goal of these diagrams is not to make some fancy-looking diagram that no one can understand. The goal of the diagram is to make it clear for somebody that everybody can understand and what's going on. Generally, the conventions are time goes from left to right and top to bottom in some sort of flowing. So it's not clear in this diagram if C precedes E before or after D, right? Because C is before D, E is after both of them. So that's where you get a little bit of it's after both, as opposed to if they were vertically aligned, you might be implying it could be others. So if I had C going to D and E and C and D were lined up. So you might have something like that, but my view is don't be overly pedantic about it. It's really just trying to show stuff together. It's important when we draw these that we're talking about variables, not values of variables, right? So I can talk about complexity or parallelism. I can talk about processors, okay, but not particular values. So I wouldn't say something like O of n or 128 nodes, right? Or an Intel XXX whatever processor, right? That's not a value. Causality is about a broad class of variables impacting variables, not the value. Because in fact, for some things, if when I change the value, the causality stops to happen, then the causality isn't about the variables. It's something about that specific value of the variable, which is a different category. So in which case we wouldn't use these kinds of drawings. So a couple other things about drawing it. In drawing this, we never have bidirectional arrows. I've seen this in a few theses. It makes no sense at all to have a causality diagram. I have seen people draw them slightly confusing, but it's possible to have this, AD, BA, as long as on this arc we have something like odd, even, right, where the variables here partition the space so that I can't go both ways at the same time. If I'm here, I can go this way when it's odd. If I'm here, I can go this way when it's even, right? Then that's a perfectly good cycle of causality. When, for example, if the state of the variable is, if the process is adding 1 and I'm here, and I add 1, I move here. And I add 1, I move here, right? So if A and B were states of the state of being an odd number, the state of being an even number, right? Then there's a causal, if my process is increments, right? So there's a place you can have this. But you never have a single error going back and forth. That just confuses people because there has to be some limit. When we have a diagram, you'll see some of them, you'll see them with labeled arcs. I don't actually have it in this drawing, but labeled arcs mean this is defining the condition in which this arc is true. Another variation is when there's an arrow with a question mark. The arrow with a question mark means this is part of our hypothesis. We're not sure. We want to test whether or not there's causality there. And an arrow that doesn't have this comes from your underlying theory, right? And your experiment then is really trying to deal with the question marks, not the rest of them. Okay? If I have this, I can extend this to say, well, maybe it's even, and that's what I'm testing. So I can put a question mark and a label to put the two together. Okay. So these kind of diagrams are found a lot in causal inference papers, in AI. They're found in various sort of process diagrams for computational X, biology, whatever, where we're often the theories from a computational point of view are driven by the underlying field. Right? So I have causal relationships. So in computer vision, right, we have a whole bunch of photogrammetry stuff that would say if this is true, this must be true. Now, notice it doesn't actually say that in this diagram, I'm not saying A is true. I'm sort of saying if C happens, then A will happen. Whether or not C happens is a different question. So the theory is connecting them only when this is true. And that's true of all causal diagrams and all inference variables, and it causes lots of students difficulty when they're trying to understand computer science. If I have the statement, if A, then B, that is a statement of causality. If A is true, then B is true. So what do I know if B is true? Well, in this diagram, if B is true, okay, so oddly enough, I can't actually say that, okay, and this is the problem, right? This causal diagram isn't necessarily complete. It describes what we know about the world. It doesn't say there's no other way for B to be true. It just says if these things are true, B is true, right? D could also make B be true, right? The fact that B is true doesn't tell me anything about A and C. Okay, this is a classic logic fallacy that if I see the antecedent, I believe the precedent is true, right? If A, then B tells me, if B is true, B is true. That's all I know. I know nothing about A, okay? In fact, if I say if A, then B, if B is always true, then if A, then B is also always true because B is always true, okay? Unfortunately, it's not actually shows in causality because if not A, then B. So a classic way when you're dealing with these kinds of diagrams to start testing stuff is to ask the same question when I replace A with not A. And if it's true for A and for not A, what does it tell me about A's role in causality? It's not A. Or sorry, oh, that's a bad choice. A is not involved in causality, right? If both A leads to B and not A leads to B, then B doesn't depend on A in any way. So it goes away. So the types of evidence relevant to trying to decide these causal relationships, this is what we call a condition of concatenant variation, which is evidence that a strong association exists between action and observed outcome. This, for example, occurs in lots of studies with human reaction time for HCI and some others. So if every time I show you this response, there is a delayed response of 150 milliseconds before this next thing happens from the subjects, right, then there's a condition of concatenant variation. Not only does A follow B, but it follows B in a precise manner, right? So it's a little tricky to say I'm going to have not A, but maybe what I can do is I can vary when A happens, and then I can look to see when does B happen. And if they move together in time, now I have a much stronger belief that B really is caused by A, because whenever A happens, B follows it by some fixed amount of time. So if I'm looking at a system that's operating, and this is the way in security, there's a whole bunch of things that are these weird kinds of attacks, right? So like a power analysis attack. I can actually figure out elements of an RSA key by monitoring the power utilization of the CPU when it's doing certain calculations. Because if the calculation has a certain kind of block, the CPU will use more power. If it has another kind of block, it'll do, so that I can just send things at it, and I can do a power attack where I send it things that will decode one way and break it up another way, and figure out literally in what part of the code does it break and help understand what's going on. So there's a whole bunch of these weird things that actually are causal in time and therefore have this relationship. The condition of time order occurrence, evidence that an action precedes the outcome. This is much weaker than the concatenant of variation because now it's just it follows. But if sometimes it follows by half a second and sometimes it follows by 10 seconds, right, it's not very clear that there's a relationship. It's still plausible but weak. And then evidence of competing causal explanations. Evidence that there's no strong competing relationship, that a higher level internal variable exists, right? And this is very hard to do because you can't explore the space of all possible explanations, right? But you can, and this is common within the more theoretical, say, crypto space, where you say, here is the scope of what we're going to allow to be considered, and given only these choices, then nothing else could be causing this, okay? Doesn't mean nothing else can cause it, it's just within the scope of these. So you often do this evidence by a combination of assumptions and then an analysis to sort of show what's going on. For lots of issues in computer science, the order of time occurrence is a bad idea. Simply never behave on it. It shows up in places where you really, to be honest, can't control the variable. So if I'm trying to look at causal inference in the behavior of a team of people in the software engineering sense, you know what? I can't always control those people. So it's hard to induce a change at a fixed amount of time and then measure it sometime later to sort of see what goes on. On the other hand, anything that's truly, purely computational, you can look for this concatenant time because you can introduce it, right? Because the computers aren't particularly random. But the more random world things they interact with, the more variation you're going to get. So the difference between these two is all about controlling variance, which is part we talked about last time, where you try and choose your variables in your structure so you can reduce the variance to the point where you can make a statistical determination that you are not being caused by random variations and the relationships are strongly tied. That still doesn't get you out of this last category, right? We have the ice cream and the swimming example, or the CPU and the throttling, and the hard disk failure, right? Temperature causes all four of those, right? Higher temperatures increase the amount of swimming people do, increase how much ice cream they do, increase how often disk drives fail, right? So we really don't want to be deciding just because we can measure a strong variation. Concaminant variations will actually exist. Hard drives don't fail as fast as people eat ice cream, right? So disk drive failures might go up 2 to 3 days after a surge in ice cream eating. Consistently. Why? Because it takes 2 or 3 days of constant heat for the thing to start failing, and the ice cream surges on the day it gets hot, right? So it doesn't always mean that's sufficient. So you want to look for some higher level arguments. So when we're looking at the experimental design, we're going to start with things involving humans somewhere. So any experiment that uses human input, human factors analysis, all of those things, and then we'll talk about some pure computational experiments, because pure computational experiments are actually easier, but they will still use a subset of them. And many things that we think of as pure computational experiments turn out to not be pure computational inputs or experiments. Because if I used inputs that came from humans, it's not purely computational, because the inputs are from humans, which means humans were actually part of this process. We have to ask ourselves, should the experiment be performed in a laboratory setting or in the field? What do you think is the key about answering that question? In the laboratory or in the field? Well, no, so we're trying to design the experiment. So the question is, what are the issues in trying to decide between doing it in a laboratory setting or doing it in the field? Not in the laboratory. So out in the grass, out in the parking lot. So think of it as, so in the laboratory or in the real world?
Okay. Does it come down to controlling the variables then? So
yeah, so there's, so in the real world, it's really hard to control everything. So that's a huge difference. Anything else?
Your assumptions.
Yeah. So oddly enough, the real world is, the laboratory has to make a bunch of assumptions about what's going to go on. And to be honest, the real world is even a strong statement, because the real world of Colorado Springs is not the same as the real world of New York, if I'm talking about autonomous driving, right? So depending on the problem, the real world or the field keeps changing as well. So there's a big question about those assumptions. Anything else?
So maybe both of them, you might want to design the first designs in the lab, and then do the final experiment test.
So, in fact, so related to that is, so we actually talked last week about one of the first things you want to do before you do any good experiment is do a pilot study. Okay, pilot studies should almost always start in the lab. Then you might do an in the real world pilot study, right? Because if you can't get it to work in a pilot study, it probably isn't going to work in the real world, right? So I mean that's a good first step. So you can view an experiment not as an experiment, but as a sequence. A pilot study in the lab, then maybe a larger study in the lab, then a pilot study in the real world, larger study in the real world. So besides the fact that I have added control in the lab, so if I can't get the controls to work, does that mean it won't work in the real world? So I have more control in the lab. Might it work in the real world but not in the lab? If so, why?
there's external factors in the world that you don't have in the lab.
Right. So there's lots of experiments that actually, when you say in the lab, you have to be very careful. So if I wanted to do high-speed photography in this room, do you think it would work very well? If I do an experiment that's going to use very high shutter speeds and look at this world, does anyone know what these lights do? Right? These are fluorescent lights. 60 times a second, this light is turning off. We don't see it. But if I run with a fast enough shutter, there will be times when this room looks really dark. And then in the next frame, it'll look really bright. You can get all kinds of bizarre behavior in your laboratory that you would never get outside, where the sun is an absolutely continuous light source. Right? So the answer to is the lab better or worse in the field? It depends on the assumptions and how well those are mirroring what's really going on in the real world. So just because it fails in the lab doesn't mean you should say it'll fail in the real world. You need to be understanding from a causal point of view what's causing my failures, what's going on, and how can we deal with that. But there's one other big difference between the laboratory and the field or the real world that no one's talked about. It's not absolutely inherent, but in general, it's almost always a big deciding factor. Cost, right? To run an experiment in the lab is normally much easier for me to control everything, which makes it easier for me to control the cost. Right? If I go out into the real world, it's generally a much more expensive experiment, which is another reason to do that pilot experiment in the lab, check things out before I go and try and deal with the real world and all of its complexities. Okay? So that's an important thing. Especially before you go out into the real world, but even before you do the lab, you want to talk about the internal and the external threats to the validity of the experiment and how we can control for those threats to make sure our experiment is valid. Okay, we talked a little bit about these validity stuff 2 sections ago. Does anyone remember what does it mean for something to be an internal or an external threat to the validity? We didn't actually define it then. We just briefly mentioned the word. So can you think of any examples of something that's either an internal or external threat to the validity? So classic internal threats to validity are either assumptions I make that are simply false, right? In which case the whole experiment may be invalid, okay? Or things that I do in my experiments that don't actually do what I thought. So if I, for example, set my CPU clock, right? But I ignore the fact that my CPU has a burst mode, right? Then I actually haven't controlled my CPU clock, right? And I have a significant threat to my internal validity of my experiment because I said I'm running at this clock frequency, but really it means it's bursting. And if I don't control when it bursts or if it can burst, then I don't really know what my experiment did. Right? And it might be the difference between one outcome and another is not that one algorithm is actually more efficient in the true sense of efficiency, but one algorithm was better able to make use of the burstiness of my clock cycles that another couldn't. Okay? Similar things would be if I use a compiler that limits my parallelization ability, right? And I'm talking about parallelizing, but I use a compiler that actually can't use the vector instructions, right? Then I might not even see the effect I'm looking for because my tools aren't doing what I assume. So that comes back, both of these are examples of violated assumptions, but they're often assumptions you're not even stating. In fact, I think those are the most insidious mistakes that happen in experiments. Very rarely will people say, I assume X, and X is not true. Because if they took the time to state it, they probably thought about it. Although there's a few of those. They'll say, I assume this is Gaussian. That one shows up a lot and is not true all the time. But most other things, if they say, I assume this number is positive, this number is probably positive. If I say, I assume I control the clock, they probably did, but maybe not. So these unstated assumptions, if you remember back to when you were reading, I said that's the biggest risk for most papers, is not that the math from this line to this line is wrong. It's that the math from this line to this line assumes something which actually isn't true. Right? That's where you run into the problem. The unstated assumptions are the most difficult part for your internal variability. So what do you think might be an external threat? Anyone think of one? So obviously that means they're outside of your experiment. Right? So it's not something you design, something that happens. But if your experiment, for example, is, again, playing with CPU frequencies, and you don't know it, but someone's changing the thermostats, so the jobs during the day have a higher temperature than the jobs at night, you again will see effects that are no longer valid, even though you absolutely did control the clock frequency in what you said. You said the clock will always run at this. Well, it turns out that thermal throttling happens, and you change the temperatures, then it may go faster or slower. And again, you see these artifacts. Lots of other external threats are things that have to do with you assume the data came this way, and the data doesn't come that way. Right? So you assume, for example, about GPS coordinates, right? But GPS coordinates actually depend on weather, right? The amount of error you get in GPS is a function of the satellite's communications coming down. So when the air is moister, the satellite going through the moisture air goes slightly slower than the one going through clearer air, and you think you're shifted a little bit in space. There's a whole bunch of things that can affect external variability that you hadn't really thought about. So you want to think about all those when you're designing your experiments. The more you can think about, this could cause a problem, and here's how I solve it, the better off you will be. For lots of other computer things, some other external threats are external traffic. right? You might actually be thinking everything is going fine and you're measuring something in your network, but if there's a lot of other traffic on the network, it might affect you in ways you're not even thinking of, like literally the firewall is taking longer to respond, or DNS takes longer to respond, not because of what you're doing, but because somebody else is hammering DNS, right? So those are, again, are external threats. You have no control of them. You might even have visibility into them. So you want to design your experiments and think, gee, if that happens, I want to handle it. So now as we go through these experimental designs, we're going to have a couple of shorthand things to try and keep it so we can describe each of these experimental designs on a page or two. So the first is O, which stands for observation, right? O for observation is measurement. X stands for exposures of the testing units in the study to some experimental manipulation, right? So we're going to cause X and look for O's. Right? X happens, we look for what we can observe. Now we're going to break the things, or the people, the subjects, the computers into groups. So we're going to have what we call an experimental group. This is the group we actually provide treatment to. So these are the people we give medicine. These are the computers that I manipulate their software. We have the control group. This is a group of people that are taking part in the experiment but aren't doing anything. So in a standard medical thing, this would be the people in the placebo group. Oddly enough, if I want to measure placebo effects, then I have to have an experimental group, a placebo group, and a control group. With the control group, I do absolutely nothing to. Or I can treat the placebo as my control group. You can do one of either. R denotes a random assignment of test units and treatments to groups. This increases reliability. I want to be very careful if I have a treatment group and an experimental group, how I decide who goes in each one. I can't take the first 20 people to show up today and put them in the experimental group and take the last 20 people and put them in the control group. Why not? So, well, but they're both 20 people from the population. Right, so there might be some reason why there's morning people and afternoon people, right? Some of them might be people that if I'm testing, right, their alertness in the morning, they're alert in the morning, and other people are just late, right? There's a whole bunch of characteristics. So the standard of this process is generally, ideally, to randomly assign people. Flip a coin, you're in the experimental group, you're in the control group. That could still possibly end up with all of the morning people, right? I can flip a coin 20 times to get it to be all heads. The odds are really low, like 2 to the 20th that it'll happen, or 2 over 1 to the 20th. 1 over 2 to the 20th that'll happen, but it's possible, just really unlikely. Although maybe mega billions or whatever it is today is a better chance. Right? So statistically, by the way, the odds are actually in favor of you making money playing Mega Millions for the first time in a very long time. If you invest $1, you are likely to win $1.00001. So, and actually, that number depends on how many people will play, but that's based on the current expectations. But most of the time, the only thing you can do in those things is you can dream, but your chance of actually winning is lower statistically. You'll always lose money at them. We're off. So M denotes things that are in both the experimental group and the control group that are matched on the basis of some relevant characteristic. So if I just randomly flip a coin and I have a population that, for example, has a lower number of women, like this class, unfortunately, right? If I randomly assign them with small numbers, I might get an imbalance where, so there's 2, 4 women today, right? So all 5 of you have a reasonable chance of being in one group. If I broke the class into 2, right? There's only 1 over 2 to the 5th, right? So if I made the groups, that might just happen. So sometimes what you do is you actually do what's called matching. And I can sort of say, okay, I'm going to take subgroups. I want to make sure that my 2 groups have equal representation of women. And I want to make sure they have equal representation, say, of age, right? Then what I do is I don't flip one coin. I flip what are called match coins. You come in, I put you in a group, and within this group, I can sort of say this is going to go on. This is pretty common in physical human studies. If, for example, I randomly assign, and I'm doing a small group of, say, 20, and I randomly assign people to 2 things, I might get very different age, gender, weight, or whatever. So sometimes I try and match people by making a small number of bins, and I take, especially if I'm trying to study weight, for example, I don't want all the heavy people in one group or the other. I want to mix, so I flip coins for them. And so you have a more complicated flipping process to match people. This is also very true in human factor studies if I'm trying to, for example, deal with experts and non-experts, you don't want to randomly assign them. You want sort of balanced numbers of experts. So you randomly assign experts separately from novices into your populations and sort of do them that way. The most complicated matches are where you actually take dozens of variables, which is only true if you have hundreds of subjects, and you sort of say, okay, here is the closest person to this person. Put one in this group, one in this group. Here's the closest person to this person. So you randomly choose a person, and then of all the people who have not been assigned, you find the closest matching person. For example, in age, socioeconomic status, GPA, lots of education studies do this, where you find the perfectly matched or closest matched person, and you put them together. So it's not even like random sample. It's randomly choose one person, find their match. Randomly choose a person, find their match, which is why it's called matched characteristics. Okay, so now we're finally getting on to the types of experimental designs. So the first we're going to start with, these are what are called classic experimental designs. They really only consider treatment level at one variable at a time. So I'm allowed to change one independent variable, one treatment. That's it. Okay, they're classical. They've been used for literally hundreds of years, thousands of years probably. So more than 1,000, but maybe not thousands. But I guess they've been around a long time. This is the oldest form of stuff. So it goes back. So the Greeks actually used this concept in there. So I guess that's thousands, right? In sort of their designs. The next group, way more recent, are what are called statistical. They allow for examining the impact of different variables, an independent variable on two or more an independent variable on two or more dependent variable. Okay. Impact of different treatment levels of an independent variable and the impact of two or more. So we can do statistics with one variable and various levels of impact, or we can do multiple variables at the same time. And we'll look through some of those. So we're going to go through a whole bunch of these. I'm actually only going to talk about the ones in blue. I'm just going to put some of these others up and mention they're out here. So there are some things in the classical design group that are called pre-experimental design. And I do want to mention these, but we're not going to spend a lot of time on them because they're not really good designs. So I don't want to talk about them too much, but I want you to know about them. So if you see these words, you don't say, oh, that's one I haven't heard of. That must be really good. These are ones you haven't heard of because they're really bad. So one group only after design. So what this means is I have one group. I don't have an experimental group and a control group. I just have an experimental group, and I measure things after the experiment's done. Okay? This is probably the single most common bad design, right? Which is I didn't actually measure anything, right? I said, here's my group of people. I showed them my software, and they liked it. Okay? There's nothing experimental about that, right? That's not a proper experiment. Now, if I actually had a bunch of people, some of whom were sick, and I gave them medicine, and after the medicine, right, they were all better, that's good. So the only way this experimental design makes some sense is if I know that there's a good chance, if I sample 100 people, one of them has some illness, and then I treat them all, and none of them have the illness, right? I've increased the chance that this treatment actually does work. So it gets used a few times in ways that make sense, but most of the time it's just a bad idea. Even stupider is the one group the non-matched control group, the last one on this list, right? Where now I say, I'm going to have a control group, right? But I'm not going to match them. So I'm going to take all of the healthy people, and I'm going to give them medicine. And I'm going to take all of the sick people, and I'm not going to give them medicine. Okay? And I'm going to call them the control group. Guess what? The medicine really works. Right? And if you think this is not something people would do, there have been dozens of studies which implicitly, not explicitly, ended up doing this. By having incentives, for example, for doctors, by grading doctors on how many of their patients survive, you induce this kind of design because they measure, well, this doctor has a 95% survival rate. Well, this doctor has a 50% survival rate, right? And it sounds like, okay, you're measuring survival after they're done. The problem is the process actually, if the process involves the doctors getting to choose who to treat, then the doctors who say, I'm not going to take on any sick patients will have a really high survival rate. And the doctors who take on the sickest patients might have the worst survival rate. But this isn't measuring it that way, right? It's measuring their survival rates, right? So the doctor who helped people, if he hadn't helped them, like 5% of them might have survived, but with his help, 50% survived. With the doctor who has a 95% survival rate, maybe if he hadn't helped them, maybe 100% would have survived, right? And he actually got a couple of them sick. We don't know, right? So this idea of not having a matched control group, you can draw any conclusion you want by intentionally mischoosing the control group. And if you don't know what you're doing when you're matching them, you can unintentionally do them. I don't know any studies that are considered valid that have ever done the intentionally. But in the world of marketing where companies pay to get stuff done, I'll bet there have been some where there's some manipulation of who goes in what group just to have them happen. Another pre-experimental design, which actually isn't so bad, is one group and what we call a before and after design. It's actually used in places where it is considered unethical to deny people treatment, or it's used in situations where, for other statutory reasons, we can't. So, for example, a number of education processes say schools have to treat students approximately equivalent. So I can't say, I'm going to take a bunch of you and say, we're going to run an experiment. Some of you get this class in, say, linear algebra, and some of you don't. And then we're going to see how well you fare, right? We just can't do that, right? So, but what we can do is and this is a common thing in schools, to measure your knowledge before a class and your knowledge after a class, right? That's a before and after design. It's very, very common in the education space. It's just not much of a design because if you're going to get down that path, there's nothing to consider. Before, you measure after, you can still do statistics. The nice thing about before and after designs is what kind of test can I do? Statistical test. There are two that are extremely common in this category. Well, I can always measure mean and standard deviation. Those are not statistical tests. Those are quantitative variables that measure for my data. What test might I do? Okay, what kind of t-test? Paired t-test. Okay, so when you see these before and after designs, you'll almost always see people using the paired t-test or the non-parametric Walshall-Kershaw version of the test, right, which is the non-parametric version. But that's the nice thing about at least doing a before-after design. To be honest, in lots of computer science, you can do paired t-tests without doing a one group. You can do a control group and a non-control group. But if you're doing things where it's actually very expensive to measure or nearly impossible, so in lots of software engineering experiments, this is really your only choice. Again, you can't go to a company and say, we're going to run this same project twice. Right? We're going to run it this way, we're going to run it that way, and we're going to measure what happens. The answer for almost all matters will be, no, you're not. Right? But what you can do is you can measure sort of the state of things before the project and the state of things after the project and sort of see how they transition. So you can do some of that. So it's not like it's not useful. That one group before, one group after design is reasonably okay when you have no other choice. So classic design. Oops. Dang. I didn't realize I was talking about all this without updating my slides. So one group only after design. I have my experimental group. I do something, I reserve the results. And avoid this at all, if at all possible. And we already talked about why. There's a whole bunch of things that this doesn't address, right? It can happen for almost any reason. So don't do that one. Non-matched control groups. You want to introduce the control group for history and maturation. So I have experimental group and an outcome. I have a control group and an outcome. But as I already went through, right, this causes all kinds of problems. The matched control group. So we match them on control groups to reduce the random selection bias. So I have my experimental group that's matched with my outcome group. Now I have my control group, right? And I get some outcomes. And if I do that, or I do the one group before after, I'm just going to catch up because I did all these already. So ideally you want to combine those. So for these pre-classic things, some of the threats to experimental validity. So the before measure effect. Anything I do may change the response because the respondents know that they're being studied. This is a particularly annoying thing in various human factor studies. The people testing the ribbon knew they were selected to test the new ribbon for Microsoft. Okay, maybe that influenced their behavior and their attitudes about whether or not this was a good change. So people will often go through things and they will choose the result that they consider to be the more socially desirable behavior. Because especially if they can be observed by others, all of a sudden you don't want to be honest. You don't want to say what you really think because you're worried what other people will do this. In studying the outcomes of juries, so if I have a bunch of jurors, these are college students and almost all psych experiments, that are from the same school, and I give them the same set of facts as certain cases, right? They are more likely to reach an incorrect decision as if I added even one student from a different school. That one student changes the social dynamic to the point that the group with the one student will help the group get the solution more often, because the social desirability of not wanting to offend people makes a huge difference, right? So that's the sort of before measure and the social effects are very important. Another one, which is very common in studies where you're using human factors, what's called the mortality effect, because in real studies, if I, for example, want to measure whether or not a particular drug helps reduce weight, and 20% of the experimental group dies, but none of the control group dies. Okay? If in fact the people who were heaviest died, and I just measure the outcome, the average weight of the people, I get very bad results. It's called the mortality effect because really people stop participating in early experiments. It was about people died, but overall we just call it the mortality effect, or more politely, the dropout effect. If people drop out of your experiment because they think the ribbon is stupid and they just can't keep testing it for another couple of weeks, but you only measure the happiness of the people who finish, you have a dropout effect. So that's a very important thing you got to worry about. Instrumentation effects. This one is particularly annoying. Results that change from changes in the measuring instrument. If those running the ribbon are running on bigger, faster computers than those not running the ribbon, obviously you have a very biased effect. But another one which is more difficult is you're in the middle of an experiment. We're doing a joint psych vision experiment for over 2 years now, right? Along the way, we actually had to upgrade the computers because campus said, we will no longer support those computers. So we went from Windows 7 to Windows 10. We had no choice because campus said, you can't keep running them. Well, I could have, but campus, they were maintained in psych. So, right? So that, we have no idea if that change in experimentation, right, would affect our outcomes. But luckily, we designed our experiment to minimize those effects because the user never actually interacted directly with the operating system. We had our own code, it was up and running, and all we had to do was port our code, make sure it ran under Windows 10, and everything else was fine. So you designed to try and minimize those kinds of things by thinking about what might be our validity. If we actually had people log in and go find the icon and start it up, we'd have had a lot more difficulty with the change because obviously how you started things up in Windows 7 and Windows 10 changed a little bit while the menus are set up. Okay, so those are the pre-classical designs. One of which I sort of recommend, the pre-post, if you have no choice, it's the only one you can afford to run. Any questions on pre-classical designs? Okay, so true experimental designs. So in true experimental designs, we adopt random assignment and use one or more control groups. And this is why they're called true experimental designs, because we're actually going to have it as a design that says people go in one group or the other. We're going to start with random assignment. For any given assignment to a treatment, every member of the universe has an equal probability of being chosen for that assignment. That's the standard definition. We're going to get to modifying that in a second. So you can modify it under certain subcategories, which I briefly talked about. So if I have what's called a two-group before-after design, this is pretty much the classical scientific study used in most scientific studies. And so how many of you are aware of like the whole EPA science fight that was going on? Anyone notice? It's actually been downplayed, but they had this issue about what they called secret science, and deep within that was another thing about these sort of true experimental designs. They wanted to say we will only accept studies that had public data and true experimental designs. Okay? And so I wrote letters to our congressmen and other people in Washington because this is a really stupid idea. Why do you think I don't want true experimental designs for things related to, say, climatology. Yeah, well, what's the control planet, right? Where's that one, right? Where do I get to say this one? So you can only, so there are controlled studies in climatology, but they're all done in the lab where you sort of say, here's a complete box, and I can measure a lot of stuff in this box. But if that's the only thing I can do, I can't ever talk about the real world, right? And so there's difficulty. So, but for medicine, this is by far the de facto standard. If you do anything in the field of medical imaging, medical processes or whatever, you need to go through this kind of process to validate what you're doing, or the FDA is pretty much going to make it nearly impossible for you to get stuff out. The only time they don't make you do this is if it would be unethical to make people not use your treatment. And this is actually, I think the only time that will happen is if the FDA has prior data that sort of says, okay, we're going to skip this design because the early experiment. But normally what happens is in the middle of the experiment, they say, these results are so significant, you can stop doing that and just move to before-after control group or whatever. So because we have a control group and we do things before and after, we are now really measuring things where it's the same person before and the same person after. So all the personal effects that might be affected by my age, my weight, everything else, as a person are controlled by the before and after. And if there are other variables I don't know about, and that's the important thing, they're controlled for by the random assignment, right? So if the fact I'm a morning person actually is important, it's randomly. They're going to be split between the two groups. So we won't be seeing that effect as opposed to any other kind of thing. If they're geographic, right, I won't be seeing a northern versus southern effect, right? So very often when you run these designs, you run them in multiple locations. Otherwise, they have some problems. So this sort of, finally, another random one that was bad. Two-group after-only design. In this case, and this is common in some medical studies, where I, for example, want to look at the relationship between, for medical studies, like pollution and cancer, right? Again, I'm not going to go out and I'm not going to induce cancer-causing agents into these people, right? But what I can do is I can really sort of do what we call a randomization can match the test and control groups on all dimensions simultaneously except for one. So I can match them on populations and say, these are the people that were close to the nuclear power plant, these are the people that were not close to it, and then I choose people that match on every other variable. How much money they have, you know, how much they work, or you match them on a whole bunch of variables, then you can start to draw interesting conclusions. Two-group after-only designs are actually also common in human factor studies and computer science, and especially in software engineering, because again, I can't go make controls, but I can take two projects that are similar from a company, and I can study them, putting one in this group, one in that group. In a cybersecurity point of view, I don't want to say, okay, we're gonna, you're gonna be an organization that doesn't get security, and you get one. We can't design them and do before and after, and very often it's hard to do the before for the same group, but what we can do is we can sort of match them. These are the groups that had none, these are the groups that had security. We can measure their effects between them. Right? So there's lots of places where these can come in. So this is pretty useful in computer science experiments as well. So we're going to have our experimental group, and we're going to randomly assign people who are matched, right? So we're not assigning them by what they do. Now, what's the problem with this? So why is this not a good idea? Or what is the threat to validity for this?
Because in the real world, it might not be the same way.
Well, that's always the case, but the real question is why might this not be a good model for the real world? Again, let's say I use that security example, right? After the fact, we go back, we analyze those people who had Norton virus versus those people that had not Norton virus, and we analyze what the security, what the implications were, how often were they breached or whatever, right? What would be a bad part of that kind of design? So one thing is, so from an external validity point of view, you assume they were both equally likely targets, right? But maybe they're not. Maybe the people that were more likely targets decided we're more likely targets, we need more protection, right? And maybe they really are more likely targets. So therefore, that kind of thing would just completely break this apart. So in doing this, you're really assuming that there's no interaction effect between the testing and what put people in groups. Effectively, people self-selected to be in one group or the other, and then we match them after the fact. But that matching may not actually effectively capture why they chose to be in one group and another, right? So I can match companies on dollars, number of employees, number of locations, but that doesn't necessarily match them on the security risk. And if that's what mattered in that experiment, then I can get some very bad results. So if you're going to do two-group after-only design, what do you think is the most important thing to make sure this experiment is valid? No, it's not that I truly randomize. What do you think? So what went wrong in the example we just went through? The groups weren't balanced because they self-selected to be in some category or another, right? So how would I change that? Well, so randomizing it, all right, so if all of the people that were likely targets chose to have security, and all the people that aren't targets chose not to have security, right? I might actually reach the likely conclusion that having security is bad because it increased your chances of being a breach, right? So how might I actually try and solve that? It's not a question of randomization. Well, in this case, they're not necessarily aware of the experiment, right? The experiment is done after the fact. This after-only design is mostly done in what might be called a retrospective study. I didn't go out and do something. I gathered data about things, and then I'm analyzing it.
You identify ahead of time?
Well, so more secure or not secure, if I'm trying to test, is this variable affecting security?
Well, I mean, like if you want to compare it, I guess you can determine if the one group is already compared to the other one. You do that ahead of time and measure that?
Well, but we had those that were prepared and those that weren't, and then we randomly assigned some of those, right, to each group, right? So that's not quite the same.
Is it in the identified right dimensions?
Right, so in the right dimensions and the right metrics for matching, right? So the one bad thing about this, which is why it is so often misused, is that the only way to really solve this, if people are self-selecting, then the two groups can't be treated uniformly, right? So if all of the people who are actual targets, right, if every one of them added security, I can't then balance groups by saying put them in these two categories because everybody who did this is at risk and everybody who didn't. So I would have to decide, if I define the dimension of what is the security risk that an expert would say this industry would face or this business would face, I have to match them on that, right? And so it's a little bit like what I said when I was talking about matching earlier. You find here is the company that was at risk that didn't add security. Now let's find an equally balanced company in terms of size, footprint, a bunch of other. So you got to choose the right variables to drive the matching. And the unfortunate part, and why lots of people don't like this, is it might mean that lots of your data cannot be used because there's an inherent imbalance. Self-selection led to a bunch of these people saying, I'm protecting myself. So there's not many people who are high targets who are unprotected. So I might have to survey 1,000 companies and only get to use 50 of them. And people don't like that. They want to use all the data. So then they mess their experimental design up, and you have to be very careful about that. So that's the real problem with that aspect. So coming back to the pre-test, post-test. So as I already mentioned, right, if you're going to do the paired t-test or Wilcoxon-Marshall test, whatever that is, right, this one from the statistics point of view is pretty straightforward. The real weakness is there's no comparison or control group. But this might be the kind of thing where if I were to look at a security point of view, I could say, here's how many companies had this before they installed the security process. Here's their breaches. After the security process, here's their breaches. Okay. Why might that fail from a security analysis point of view? Even though I did pre-test, post-test, right? What's the potential threat to validity of that experiment? Oh yeah, so you can definitely, it's like, well, our security is we're going to go to what we used to jokingly call C4 security, right? Your computer is like, if it gets attacked, it just blows up. Well, it's gone, but you can't do anything with it. Right? My mom worked for a crypto security group that literally, that was part of what the government made them design, is that if the crypto chip was opened, it had to self-destruct. It didn't actually blow up. It just like electrically destroyed itself, so you couldn't do anything with it. So that would be one possibility, is that there's some weirdness. But let's let that go. What else could be wrong with if I do a pre and post test for this group and there's no control group? Well, there could have been something else, right? So, for example, right, and this is in the security space. How many of you have ever heard of the broken window theory of whatever, right? So, the broken window theory missed some really important things. So, I was in New York at the time, right? Things did get better, but things got better in every city, right? Because, in fact, crime overall went down. So, if crime is going down in every city, then it's going to go down in mine. And this pre to post and saying, well, we're doing this broken window in the middle, right, to get rid of the minor things. If it's just going to get better anyhow, that's back to the cold remedies and whatever. There's lots of things that they're all related. So pre and post doesn't show causality because other things might be driving it. And in a very large population, lots of those things will happen. If I do pre and post test with a control group, which I mentioned but I didn't go through. So this one becomes more difficult because I have two groups, control and experiment. So I can't just do a t-test. Right? Now I actually do have something that's called ACNOVA. I can do multiple t-tests, but what goes wrong if I do multiple t-tests? And what do I have to do to fix it? 20 jelly beans? What went wrong? Green jelly beans, right? So they cause acne or whatever it was, right? With a statistical test, you're looking at the probability that test can go wrong. If I run lots of them, right, I can change the interpretation of that. So we have this thing called the Bonferré correction to adjust for that, and you can adjust for it. ACNOVA is actually an even better test, and ANCOVA, whatever, right? It's like ANOVA, but it's going to use data from the pre-test and the post-test to help decorrelate the reaction to variables. I'm not going to go into detail of that, but if you ever get into something where you have a lot of variation, so your two groups are controlled, but if those groups themselves have lots of variance, it is sometimes very difficult to reach a conclusion because the two groups are varying. Right? So we already talked about this for the t-test, right? If I have two performance curves, right, and I match them up this way, right, I can get that this group is better than that group. Okay? But if instead of something like this, I actually have sort of a band where these people behave like this and these people behave like that, it becomes impossible to do it with just the t-test because every sample now itself has a variance. We looked at that when we were looking at the sort of COSTO or whatever. So a couple of things you can do there. You can change the variables before you do your t-test to inherently try and reduce the variability by, instead of measuring a variable that has multiple dependencies, to redefine the variables to reduce those dependencies and then measure them that way. And that's a little bit of what the ANCOVA does. It'll actually help tell you what variables you could deal with. So things get more, classical designs become much more complicated, and I have no idea why this slide's going upside down, but okay. If I want to deal with things where there's time series, so there's a lot more data over many time, so I can have an experimental group with a whole bunch of observations. This can be more useful and more difficult at the same time because it's very hard to do these and at every time step do random assignment. Right? If I want to do somebody's going to come in. So in our psych experiment, we have like 9 measurements. Somebody comes in. So people are assigned to one of 2 random control groups. But then we get video measurements continuously over a period. Right? There's no way for me to say, okay, after 2 seconds, we're going to switch who's in each control group and keep switching back any sort of time series. Right? Time series have to be measured over a period of time. So you're going to get a whole bunch of things. But the nice thing is, if you have a time series, there's a whole lot more measurements and sort of this sort of idea of pre and post. You can't just do t-tests. I can't take each of these and treat it as pre and post, pre-post, whatever, without the right corrections, because I get all kinds of errors out of that. But, there's another thing called trend studies, which is related, which is really measurements over time from a succession, but now of sort of random samples. So if I actually look at things like the number of processes running on my computer, right, and what process is using CPU time or memory, right, that's a kind of trend study. Over time, it's changing, and I'm sampling, right, because when I stop the CPU clock and I look at what processors are where, that's a random sample in time. It's not completely decorrelated, but it's a random sample from the population. There's some other things that are called continuous panel studies, where I collect a series of measurements over the same period of time, and I test them over a period of time. Again, this is common if I'm doing human factors. In fact, the ribbon people trying to measure what's called the learning effect, which is a common thing to do in certain kinds of CS experiments. I want to see how quickly people learn my user interface, right? Which part of what they said the ribbon was easier to learn, which of course you have to take people who don't know how to use it, and then you got to show them, and then you're going to measure their effectiveness, and you do it again over time, and then you do it again. So again, it's a time series, but now it's groups of people put together in funny ways. So we're not going to go into those, but I just want to mention these are all things that are out there. If you ever need to do a study, part of it is go look for some of these. You can go back to these notes and find out what kinds of things are going on. Another one which can actually be relatively easy to run, a little relatively easy to analyze, and we'll come back to what its disadvantages in just a second, is what's called a completely randomized design. Within a completely randomized design, this is statistical, I basically take any treatment assigned to a test unit on a random basis, and right, I just keep doing that. I keep assigning experimental groups to various categories. Whoops. So when I do this, there is no control group because I'm not designing it to do a control. But what can I do from a statistical point of view with these outcomes? Okay, how and for what reason? So yes, I can always compare them to groups. What am I going to do with them? So one is, so if these experimental groups are all in the same experiment, then variations across this tell me something about how effective is the statistics, right? Because we talked about doing cross-validation, right? This is like cross-validation. I have a bunch of groups I can do some things. But actually, that's the problem with this. With no control group, we're back to I've got one experiment, and it's really hard to tell what's going on, especially if I'm taking any number of treatments. So think of this as I tried algorithm 1, algorithm 2, algorithm 3. Okay. Now, what's interesting in computer science is, as opposed to medical science, where this is pretty much frowned upon, in computer science, this can actually be meaningful if what I want to conclude is that experimental group 3 is better than experimental group 2, right? I can now do pairwise comparisons across these groups if I keep everything matched. So this will show up, okay? But importantly, I didn't choose which data items, right, go to which group. So if I do purely matched, it actually isn't what's called a completely randomized design, right? But if I have something that I can only process once, so I'm doing a human factor study, and I'm trying to decide which of these 3 user interfaces is more efficient. There actually isn't an interesting question of what's the control group, right? I have 3 designs. Management has already decided we're going to move forward. Which of these 3 are we going to use is the question, right? Then I can run this design, and I take people and I randomly assign them to one group or another. The simplest form of this is what we call A/B testing. People heard of A/B testing before, right? It's extremely common. So common that if you use Google for advertising, it's a built-in function now. You tell Google, go run an A/B test for me. and they will run it for you. They will say, here's one ad, here's another. We will figure out which of these ads is more effective by randomly assigning people to one group or the other. And then eventually they'll decide, we've run enough experiment to know that that ad B is better. We stop showing A. We just switch over for you automatically. You don't even have to worry about it. You set up the experiment, they'll run it, they'll decide the statistics, and then switch on. You can actually do that with Google with up to 5 different ads, which is much more in this category. And then what they're really doing is they're randomly assigning people, seeing what happens and seeing the outcomes. So this is pretty commonly used as a completely randomized design among basically a forced choice of here's n things, which one is better. Okay? But for things where we wanted to have a control, how would I modify this to have the control of the status quo? How would I use this where I want to actually have a control group of what we currently do? This is actually a very easy question. Maybe it's too tricky because it's too easy. No, X is the treatment, right? So if I just make X the current status quo, right? If X1 is what we do now, then this doesn't change anything, right? So then you have a control group. So in fact, the difference between a control group and an experimental group is how you label them, right? If this is no change, then that's a control group. If it's a change, so if X is a treatment that's no different from what we do now, it would be the same. Okay. So the problem with randomized designs is actually it takes a lot of data if I do completely randomized designs, especially if I wanted to change multiple variables at the same time. So if I want to, for example, change font size and color, right? I have 2 dimensions now. If I want 3 font sizes and 3 colors, how many randomized experiment treatment methods do I have? Well, 3 times 3 is 9. That's a lot more things to run. So the idea of what's called randomized block designs really is designed to try and match variables up so that I can do things more efficiently. So I'm going to have a randomized group and a control group, and then in another block, a randomized group and a control group. And if I do this right, I can actually ask questions about which of these made more of a difference. So I can ask by starting off, which makes more difference, font or color? Once I decide that, I can run another set of experiments within whichever was the most important group, and then say, okay, given I've chosen this font, what's the right color? Now, it's possible there's a lot more interaction effects, but very often that doesn't happen. When there's a lot of interactions, we sometimes do what's called a Latin square design. We reduce the number of groups involved when interactions between the control treatment levels and the control groups are unimportant. And this is really where I was heading with this sort of font and color. We take the same number of rows and columns as the number of treatment levels, okay, but it can't determine whether or not color and font changing simultaneously matter. Maybe small red fonts are okay, but real big red fonts are really bad. Small blue fonts are terrible, but big blue fonts are okay, right? If those 2 things are coupled, it doesn't work. But the basic idea is to sort of minimize the effects. So if I have things that go farther, and it is true for lots of computer science things and lots of education things, order matters. Once I've shown you something, I can't unshow it to you. So if you've seen it, you're affected by it. So I can't have you do the same experiment. So if I want to change fonts and colors, I can't give the same person, here's this one with a font, here's the same thing with a bigger font. Why? Because they already know the answer from the first one. Right? It's changed their effects. So whenever we want to have these kinds of effects, we have test sessions. Let's say I had 3 choices. I'd have test sessions 1, 2, and 3 with maybe 3 different questions to play. And then the subjects would go through them in one order. Subject 1 doing A, B, C. Subject 2 doing C, B, A, and or whatever they say on the screen. Right? You go through them in different orders. And from that, with a little bit of factor analysis, you can figure out what was actually driving what. So the order of variables often matters in human factors-related experiments, and it matters in some programming effects. What's an example from a programming point of view where order matters? Well, how about a battery point of view, right? You guys already know hysteresis is huge in what you're doing, right? So you can't just say, I'm going to use this charge cycle, and then I'm going to use this charge cycle, because this one may actually be impacted by the first one, right? So it's going to show up in lots of things in that space. But what's an example within computer science? Because it actually shows up frequently, and unfortunately people sometimes ignore it. Let's say I'm looking at speed of code, right?
Pipeline.
caching, right? So pipelining has a little bit of effect, but caching has a huge effect. If I preload the cache by running an experiment, and especially if you have a large, like modern cache with 20 megs in it, right? Your entire data set might fit in the cache. So like the first algorithm you run can look really slow, and the second algorithm can look blazingly fast because one's reading stuff from RAM and the other's reading stuff from cache, right? It's a common problem. So anytime you do computational experiments, you should be doing some part of that Latin design where you run this one followed by that one, then this one followed by that one. If you get the same results, your things are good, right? It's not hard to also wipe the cache in between. That will reduce the impact to sort of say, okay, I'm going to run this, then I'm going to run this program that's going to effectively purge the cache, then I'll run it again. But that comes up to you remembering that caching effects can be important. So you want to include that in your design issues. So if I've done this sort of Latin design in what's called a two-way factor analysis, we have sort of the main effect. Again, I'll use the font and color. So I would argue the main effect of readability is font size, followed by font color. So I'd have a main effect and a secondary effect, right? So my main effect, my secondary effect, I do those interactions, and then now I have like this grid, this Latin square of numbers, right? We can't do simple statistics. I mentioned one test you could do. Anyone remember what it was called? It's on the screen. It's easy. It's called ANOVA. So ANOVA is the analysis of variance, and it looks at how each of those variables can help to explain the variance. And it'll allow you to do some analysis. So of course, if I have more than two things, so for fonts, I can have font size, font color. I can also have font style, like literally what font out of a long list of fonts. Okay, Grant, now I need more dimensions, right? And this can keep going on and on. So I have to be a little careful. If I add too many dimensions, it becomes too expensive. But I can still do ANOVA with these 3 dimensions. But what do you think happens when I go to higher dimensions? What do I need to draw conclusions? So in this study with 9 or 6 cells, let's say I had 100 people. How many people would randomly show up in each cell? 100 divided by 6. Okay? Now I have 12 cells, right? I cut in half the number of people. What is that going to do to my statistics? It's going to reduce their significance, right? Unfortunately, not even in a linear way. Going from 12, so if I had, going from, with 100 people divided by 6, that's 12 or so, right? 15, something like that, right? But dividing it by 12, I'm now less than 10 people, right? My statistics at 15 is weak. My statistics at 7, really hard to draw any statistics at 7. So you might go from I can draw a conclusion to I can't. So the biggest problem as you increase this dimensionality is your number of subjects become intractable. You need lots and lots of them. So sometimes the only way to do it is to not do the study all at once, right? But to actually do it in this sort of sequential order. So we can do what are called factorial designs. So those are what are called factorial designs. You do sort of all combinations at once, right? And that's when it becomes expensive, right? But I can do them where I choose the most important variable, answer that question. Font size is the most important thing for readability. Do what I think ever is the next most important, actually font design. Then go to the last one's color. And now this is what we call, and I thought I had this in a slide, and maybe I have it later, but I forgot, but so I don't forget it. We call this one the sort of Latin cross. So before we had a Latin square. Latin square, we fill them all in. In a Latin cross, we sort of choose one dimension. This is especially true if I have lots of variables in this dimension. In this dimension, I optimize and say this is the best answer. Then I choose my next dimension, and I assume this is the right value for this other variable, and I fill out this. And then I can do another one out of the board and get my third dimension. So instead of having, if I have like 10, right, 10 cubed is a big number as opposed to 30, right, experiments. Right? So you want to think about how to break it down, and if you can sequence them. And what did I give up to do this? I can't measure anything about the interaction of those variables. All I know is I assumed that the best one is here. It might actually be that the overall best one is up here, right? this one might have bad behavior here, but much better when we get over here. This is especially true if the relationships you're looking at are highly decoupled. Right? So, in fact, certain styles of fonts might be very unreadable, right, when they're small. Right? And so, when I choose one font and I measure size, that font might have a different size. Right? So, Times Roman was designed for financial reasons to allow the highest readability they could get at the smallest font they could get in physical compactness, right? So they could print more in the newspaper because literally every extra letter you added was made the paper bigger or whatever. Arial, however, is not readable very small. It has to be bigger to be readable. So if I did this experiment with Times, I might end up here. If I did the experiment with Arial, I might end up here. Oddly enough, Times, whatever over here might be more readable than that was for Arial, right? We just don't know how they interact. So if you have complex interactions, Latin crosses are not very good. If they're truly nearly independent variables, then crosses are a much better way to go. Yes? Yeah, we'll go ahead and take a break now. Might as well. Biology says break, then we break. I thought I'd be done this by 6:15, but I'm ad-libbing too much. 6:15.
So if I'm bringing an equation in my paper, do I really need to cite a reference for it?
Is it your equation or their equation?
It's a very general equation that it's not really clear who the author is.
Oh, so if you have like
Sigmoid function.
sigmoid function, you don't have to cite the sigmoid function. That's
Thank
right.
you. Thanks. Because I just found an article written about who's the author of Sigmoid function.
So actually, it's somewhat contested, right? But that's so anything that you would find like in a standard textbook,
Exactly.
right? You really don't have to cite because it's considered
Okay.
standard knowledge.
Thank you.
If it's controversial, right? So in fact, if you want to say the sigmoid function as invented by so and so, then you need a citation because there's some display, right? But the actual sigmoid function itself, no, you don't need that.
Thank you.
Still missing a few. Unfortunately, I didn't say when to be back. Okay, still missing 2, 3, 4, 5. Okay, I'm good in a minute or two. Okay, so we're going to continue our discussion. We're almost through this. So if one can run algorithms on static data, which pretty much is lots of computer science, but not all, without any human interaction, then we can do these perfectly matched pairs. But that often makes it hard to do anything causal in such testing, right? So if we want to do causality testing or dynamic data, we really have to use a fully factorial or maybe a cross type design. So why doesn't running it on matched pairs on static data tell me anything about causality? Right. I just have data. I don't really know what's causing it. Now, I can actually change that a little bit by saying, I'm going to intentionally design my data to have this characteristic. So here's a set of data where everything is of length 10. Here's a set of data where everything is of length 14. So if I vary something about how I made my static data, I can start to get towards causality. But that means I'm actually moving towards the design. As I change font size, as I change font choice or color, right? I'm intentionally varying something about my data. So if you want causality, you really have to get into experimental design, even if everything is perfectly predictable, because you really want to be able to say, these changes cause these outcomes. And that means you got to change these things to vary and see what's going on in the outcomes. Another thing which is unfortunate but very common in computer science is you really must avoid tuning on the test data and contamination of testing data into the training process. Ideally, you should use test data exactly once. You should never run on test data twice, because if I ran on it, well, once per algorithm, right? But if I'm working in my algorithm and I say, well, you know, I didn't beat the state of the art on that test data. let me tweak my algorithm, right? Then I can make my algorithm better and better until I beat the state of the art, a process that I like to call graduate student descent instead of gradient descent, because all you really have is the graduate student is guessing what changes will make it better until I can beat the state of the art. The problem with that is it doesn't necessarily generalize. That new algorithm run on other data may not be beating it, right? You're tuning it very much to the test data set. Unfortunately, and so I cut some of my students slack. Chun Chun, one of my current students, where just finished up a paper. I grudgingly let him do this in the paper because everyone he compared to say they optimized their parameters on the test set, right? So while that's inappropriate, if it's what everyone does, sometimes it's the only way to get your paper out. And I said it was okay as long as you could say, and here's a completely automated algorithm that you can run, and this algorithm wasn't tuned on the data set, and here's how well it does. It does not do as well as the one that was optimized on the test set, but you got to start this trend. If everyone's training on the test set, or not, I wouldn't say training, they're tuning on the test set. Very few people in machine learning will actually train on the test set. But if I run it 100 times until I find the algorithm that does the best results, and I choose the best parameters, then that's a little bit of cheating. Okay. So another one where I see this from an experimental design, especially with this trying to run on static data. You run it on 15 different data sets, and you publish the 6 where you do better. And you don't mention the 9 where you did worse. Okay, not quite honest. But unfortunately, if you just ran it on 6 and you didn't even try the other 9, you might still feel good about this. I ran it on 6, it was good on all 6. Right? That's actually a really hard question. How many data sets do you have to run it on? So what you have to do is try and relate how realistic are the data sets compared to real problems. And if I chose things that are, for example, all small in size with a small number of dimensions, but the real world problems are large data sets with large dimensions, then you can't draw a strong conclusion. Right? So it's how related are it. So I was going to get into some of these, but given, well, we'll skip that one because he's out. We'll start with this one. So what kind of experimental designs do I want to do if I want to evaluate models for predicting battery charge? Right? There's 2 of you who are writing your paper on this, right? So what kind of experimental designs do you think you'd be thinking about for this? Right. So you're not actually changing the model. Are you changing the models and then using those models to charge the batteries? Or are you just trying to describe the state of charge?
Mostly trying to describe.
Okay. So given, so you're trying to have you're just trying to build a model, not make a model of how to charge.
No, we are not working on charge.
So that makes it easier and harder because, so what dependencies are that you have to worry about? Or let's say everyone else, right? It doesn't have to be just them, right? So if they're building a model for a battery that isn't in charge of how the battery is charged, what are the things they have to worry about? You can answer too, but I want everyone to be thinking about this. Some of you read their paper, right? So you have even more knowledge, but what are some independent variables and what are some threats to the external variability of this, viability? Temperature, right? So your model might be temperature sensitive, right? I would expect your model would incorporate temperature. So in that sense, that's less of an issue because you're going to have that as a model parameter. Right? Maybe. I'm not worried so much about what things affect the actual charging process, right? So you have a difficult problem because how do I get the 2 batteries to be in the same state? Right? Since your models say that hysteresis is a function, right? There's this whole question of getting all the variables, right? So if I have 2 batteries and I want to say, here's a better model than this one, I have to run them through a bunch of changes and whatever. I have to hope the batteries are actually well matched. So my experimental group and my control group have to be matched on capacity, charging history. There's a whole bunch of things that get into this to try and make that more difficult. So physical experiments in anything in dealing with physical objects, you have to be careful about controlling all of those things. Right? So not saying it's not doable, it's just you want to talk about those. And if you can't control them, then if you can't control a variable that you think might have an impact, then what do you have to do about it?
I mean, what I'm doing right now is I'm saying I have a whole
So,
Well, not really statistical average, but so I have pretty much one of the big things we're talking about is quality control on some of my cells is not very good, and so I have these cells that have different capacities and different charge curves and discharge curves, and so I'm taking all of them and saying what works most.
okay, but you have no control group, right? You have just the experimental group, right? You charge them, discharge them, and sort of see where they're at, right? So the difficulties you can run into there is because I have, so a slightly different design would be to take all the cells and match them, right? Here's the as close as I can get to match cells, right? And then I can go through different cycles and look at the differences between the matched cells, right? Again, I guess, so, but you're not actually, what's your independent variable? You're not changing anything, right?
Well, as far as I guess I don't know.
So from an experimental point of view, you're not actually saying, if I change this, this is how my system will respond. You're actually doing sort of a single group after the fact analysis, right? Here's my model.
System identification based on optimization.
Right. So there actually isn't an experimental design in that piece. That's okay. So if we're looking at evaluating adversarial examples, how do you think we would design an experiment? Right? That's what you're working on, right? Must be that. That's all. So what kind of experiment do I do to evaluate whether or not, let's say I have a technique to defend against them? Right? Isn't that part of what you're looking at? Okay. So. Right. So that's in fact where almost everyone started. And what's wrong with just saying, okay, here's the adversarials clean, and here's the raw images. What's wrong with that model? Or how do I make a better experimental design than that? I mean, what did I change? So again, this is the reason I'm doing this is in fact all of the ones I'm going to go through, right? So because we're far behind where I wanted to be, I'll just sort of cut to the chase. Lots of computer science papers, lots of modeling papers actually aren't doing experiments to try and measure causality. They are looking at data they have, and they are measuring behaviors on that data. Way more interesting is if I can sort of say, here's something I can vary, right? So for batteries, it might be that if I have fast charge versus slow charge, one model does a better job of modeling what's going on. If I have constant temperature variation, so you choose a couple things you can actually vary, and then see if your model actually predicts better or worse in those categories. I can play games with adversarials. I can play games with underwater communication. So an experiment is something where I intentionally vary some parameter, not just fit parameters after the data. Right? Because if I just fit parameters after the data, it's modeling, not experimentation. And there's a bunch of those things. So, so I already covered a bunch of these, so I'm just going to... so one of the issues with laboratory experiments, where I think we covered all of these, laboratory experiments with people tend to be extremely artificial, right? If I'm trying to say, if I ask people, how would you respond? The answer to that question is almost never how people would respond, because they're actually making a cognitive discussion of, you're asking me a question, you want to know the answer to this question. Much better is to see how people respond, even in a laboratory, rather than saying, which of these two would you choose, right? Put them in a room where no one's watching, they think there's no cameras, and watch which one they choose, right? Because there's a social implication of choosing in front of you. That changes all kinds of stuff. These are the sort of testing effects that become affected by what's going on. The good thing is it's really cheap, and it allows you the greatest control. And because of that, so field experiments, you're really sort of running things, but there's a whole bunch of things in the natural setting that can be introduced, which is both good and bad. You're testing in whatever those are, but you have to be careful. The responses will tend to be much more natural. They tend to have much greater what we call external validity, because all of the external world is better modeled. Whatever it is, you don't know what it is, but it's better modeled than in the lab. But it's also much more difficult to control. Very often there can be very different competing explanations for the results. You have to be careful about those. And I just want to I put here at the end, I'm summarizing stuff. more so that if you want to go back and review this stuff, like all of these things that can show up at the end. So threats to internal validity, history, maturation, so things get older, batteries age, testing, instrumentation, statistical regression and selection bias, how I choose my model fitting, mortality, people dropping out of them, selection and maturation interaction. So if I choose people who are more studious students, they tend to stay in the study. Right? So I have this weird interaction of those two things put together. External validity, so the kinds of things would be reactive or interaction effects of the testing. So literally, if I'm doing something with cameras, which is a common thing, I go outside, the sun will change. Go behind a cloud, whatever, instantly the whole world changes, and there's this reactive effect in terms of what's going to go on in my experiments. I get the interaction effects, the selection bias, and the experimental variable. So as I make selections in the outside world, that may affect the selection bias. So if I literally have a sign on a sidewalk and I'm trying to use that to select who will be in my experiment, if I put that sidewalk on the sidewalk between Columbine and engineering, I will get a different subset of people than if I put it between engineering and the College of Business, right? Because the students going between those two buildings are actually not the same subset. So weird things happen when I try and work in the real world and make selections. There can be all kinds of things in terms of the experimental arrangements and multiple treatment interference. So if I'm giving a person a drug and I don't know what other drugs they're taking, there's this whole drug interaction effect. If I'm running a computing experiment and I don't know what else is running on my computer, I can get all kinds of crazy effects that I'm not seeing. So, time and cost are a big limitation. There can be some security implications as well. There can be all kinds of implementation problems where you may be difficult to get cooperation of the organization. Contamination may occur because human subjects, because of inability to do the treatment, the designated environmental area. Lots of studies that try and do things like multi-layer security suffer badly because you can't actually get access to lots of the multi-layer security data and do anything with it. My student and I published a whole bunch of papers on document leak protection where the goal was to use natural language to answer the question, is this document an unclassified document, a confidential document, or a classified document? That study, he'd actually asked me about it early when he was first starting as a student. And it's like, well, we can't work on that problem because we don't have classified documents, right? We can't actually, I can make up stuff and say, well, we're going to pretend this is the classified group and this is the unclassified group. And some people had published on that. But luckily, or unluckily, there's this thing called WikiLeaks. WikiLeaks actually had really classified documents. I have never looked at them, but my student was able to analyze them and extract features and do stuff where we can actually now meaningfully say, we can actually do something like that. So access to data is critical in terms of, can you get it? And can you get the data you want in the way you need it? Variability in behavior across test units can be so large that it is extremely difficult to detect the experimental effect. This is true anytime you make a radically different change in a user interface. So if you take, the ribbon effect, right? So the ribbon study, Microsoft's, one of the internal reports actually didn't find it was better, but they accounted for that by saying, well, everyone knows the other one, so they're efficient at it, so we're going to discount that efficiency because the new one has a learning effect and we haven't gotten there. So after like 2 weeks, they're here, we expect they'll get to here, right? So you can make games to try and account for it, but large variations cause you all kinds of things. So since CS is a fundamental underpinning of the information age, we have to be very careful because our studies are really looking at our synthetic products of what humans do. We can design our studies in all kinds of ways, but we really want to be trying to model the real world. So if I do something that's too laboratory, too model-driven, I may get something that works really well. So your battery models might work really well given the test charge and discharge cycles you run them on, only to have them fail miserably on something else, because that's not the way the batteries really get charged. Or maybe they're really good on a wide range of things, as long as you don't change the temperature, right? So there's just so many variables, it's very hard to make sure we get all of these things done. The complexity that you're going to deal with in computer science projects often precludes theoretical analysis. So even if you have stuff that's theoretical oriented, you're going to need experimental analysis to get there. So The last couple pages I'm not going to spend much time on. This is my checklist for evaluation, coming back to things we talked about. What are the claims? What are you trying to prove? What is it going to look like? How do you go through this? So this is just a checklist so you can come back and look at it. And with that, I'm actually going to end this. I'm not going to, this is a joke. We actually put it up before. I'm going to skip over to the next topic. There we go. Clouds and research. So just to give us a feel for where things are going before I jump into this, we're going to be doing clouds, and I don't think I will finish everything today. So this class, I'll start talking about AWS. Next class, I will finish talking about AWS, and I will give you a very simple AWS assignment. The short version of that is you're going to have to make an AWS instance and run some simple experiment on it and produce the outputs, and then I'm going to want to see, here's my AWS run logs, which today I won't get to because it takes more than half an hour to get there. Just sort of show me you were able to get stuff running on AWS. That's really pretty much your assignment, but you're going to have to prove it all to me next week.
So it doesn't matter what the extent.
No. So this is not about what you're going to do with AWS. I want to get you all over the learning curve and the fear of, I don't know how to do it. Once you know how to do it, you will eventually get to the point in your career where you have something you want to do, and then you will know how to do it. If you don't, because I've had 4 or 5 of my students use AWS in the beginning, many were like, it's going to take me too long to learn. It's like, no, not really, right? It will save you enough time. It is worth, go learn how to do it. It's the only way to run the experiment, or sometimes it's not the only way to run the experiment, but it's a convenient way, and I'll go through some of that stuff. So we'll do AWS this class, the beginning of next class. Next class, I will also talk about how to give a research presentation, because your next assignment in this class will be to give a research presentation. You will all be giving one, which will actually take most of the rest of the semester. We're going to be looking at relatively short, 10-minute presentations. Originally, I was going to do like 30, but you're only going to get 10, which is harder than 30, even though it doesn't sound that way. 10 is harder. And if you if you have a real research topic, you actually want to talk about your research, that's fine. Otherwise, you can talk about your survey paper and sort of give a presentation about that. So you can start thinking about what's going to be. Don't worry about writing it yet, because we'll talk about what's a good presentation, what you put in it next week. And then next week, if time permits, we'll also get into what is a thesis proposal, because I know some of you really want to know that. That's part of what you were hoping to get out of this class. We've talked about writing, but not writing a proposal. We've been writing documents. So, and then after that, mostly I want to have presentations on research for the next N weeks. I've asked faculty. No other faculty besides Sung Young has volunteered. If you really want your advisor to give a research talk, prod him or her and say, you should give a research talk, right? We want other people to hear about this area of research and how that works. But otherwise, it'll just be us giving presentations. And if we do 10 minutes, we actually have like 2 weeks left. So then I don't know what I will fill in. We'll see where it goes. So now we'll talk about AWS. And if you're really good at AWS and you want to head out now, how many people have ever used AWS? Oh, okay. So this is really very basic AWS, right? I'm going to talk about why you want to do it, what you can do with it, how to spin up some instances, goes through some very basic tutorial stuff. If you guys already know this, I don't want to waste your time. I will see you next week. And we will start next week with the remainder of this. So if you show up a little bit late, I will not be holding that against you. But I know that some of you use this for work or other. And by the way, I will do everything in my examples in AWS. I also have access if you want to learn something new and you're good at AWS and you want to use Google Cloud, I can give you free credits for Google Cloud so you can do your learning there. You have to use some cloud platform. It doesn't have to be AWS, but AWS is the biggest gorilla right now, so that's what I'm going to teach at the introductory level. But otherwise, you guys want to just head on out, go ahead. I'll give you a second so we don't interrupt everybody. Okay, so the user guide for AWS can be found by Googling AWS user guide, which will take you to this URL. It changes frequently. AWS has grown very fast and continues to expand. So it's pretty hard to sort of say, well, I'm going to cover everything. There's no way. I will show you, like they already have, I don't know, 70 products or whatever on AWS, right? We're not going to even touch all of them. We're going to show you some very basic stuff to get you through. So I'm going to start with a little bit of what is cloud computing, talk about some of the benefits of using AWS, especially for your research, and then look a little bit at sort of what we might call the web services stack. What is the series of things you can run and get access to? So the basics of cloud computing, you will hear this term a lot. And really, there are three primary areas that people call cloud computing: software as a service, platform as a service, and infrastructure as a service. And I've highlighted the bottom one because for your research, unless your research is about software as a service or platform as a service, the bottom is why I think you will find Amazon AWS useful, because it is your low-cost, large-scale research infrastructure. Right? Now, if you really want to run web services or do software as a service as a company or as a product, the first one's really important. Or platform as a service for doing toolkits and whatever, all that stuff is very important. But that's more important at the business level. For your research, it is unlikely you can use software as a service as a huge part of your research. Why? Because it's already out there. It's not novel. It's not new. But there might be some things you can study about it that would be new. So I'm not saying it's not there. So one way of thinking about cloud computing is it's a scalable hardware layer. If I need one computer, I've got one computer. If I need 20, I get 20. If I need 100, I get 100. But on top of that, if I just view it in terms of hardware, it's a little bit more limited, because beyond the hardware, there are some very basic services for what we may call the grid service, the storage service, and the queue service that structure how I get data in and out. So right, it's not just how many computers I have, but how much storage is there? How fast can I get to that storage? What can I send where? Which the grid service is sort of communication. And then a queuing service that might let me actually manage large flows of information without knowing how large those flows of information are. So if I'm running an experiment and the output of one stage goes into another, the queue in between has to be big enough to hold everything. And if I know what my research is, that might be fine. If I don't, I need a queuing service to actually handle lots of things. The queue depends on how fast the computers run. So if this stage can produce data really fast and this stage consumes it much more slowly, then my queue will keep growing. And if I don't have good infrastructure, then I have to worry about the sort of natural queue. What do you guys do for a queue? Anyone know what almost everyone does for a queue when they don't think of it as a queue? Nah, that's actually looking at it as a queue. We call it the file system, right? The first stage of research writes a bunch of files, and the next stage of research reads a bunch of files. Okay, I/O, disk I/O, 10,000 to 100,000 times slower than memory transfers. So if you do it that way and you write your experiment where the first thing you're going to do is you're going to write it to disk and then you read it to the next stage, right? You've ensured a slowness in your pipeline, but it guarantees scalability because I can write a terabyte to my disk if I have a big enough disk and I don't have to worry about what's going on in my stages. So there's some flexibility. So we really want to be able to make our services so that we can automatically do things efficiently and do the queuing and whatever. As I said, there are many close choices of clouds. I'll go through. The biggest by far is Amazon at 34%. Microsoft Azure, you've probably heard of, is 13%. IBM Cloud is 8%. Google is 6%. And Alibaba was 4%. And this was as of March of 2018. Did anyone notice anything about these numbers? They don't add up to 100%. Not only do they add up to 100%, they don't add up to close to 100%. Okay. Does anyone know there's actually a big provider that's not on this list? Anyone know what that is? These are all the names you probably heard of. Alibaba I just put up there because I think Alibaba's down there, but it's a new one, but it's not. So, anyone have any idea what the other cloud providers are? Okay. So the other cloud providers, so the next biggest, in fact, the second largest cloud provider is a company called Next20. Okay? And you've never heard of them because they have, I'm not sure what the total number is, but they used to have like 40 clients. Now they probably have 80 clients, right? They only do cloud providing to really big people, right? They have no customer-facing stuff. It's all B2B, and they go after, Dell, right, is using cloud services from Next20. Now, they also use a little Amazon Web Services, but they get a lot of their stuff from Next20 because Next20 is largely dedicated, as lots of the other ISPs, so people like Comcast uses Next20 as well, right? They have this dedicated service where it is cloud, but it's not public-facing cloud. It's very focused on what they're going to do, and they're sort of a big chunk of their market. So there's a few other providers in this very specialized niche of, we are a cloud. but we're not a cloud for everybody, so you don't hear about them. So you're not their customers. But, services that are offered by these cloud providers, there's really a ton of them. As I said, I think Amazon got more than 70 different services they provide. I believe Amazon is the biggest with the widest range of services. We'll review some of them. But if you want, I'll just go ahead and click on this, and then I can't show you this because I have to break my video for a second. Well, I can do this. I can't. Well, I'm gonna have to do it. So give me a second.